嗨，各位同学好，那我们继续第3章的讨论。So welcome back to chapter 3 of electromagnetic theory. In this part, we would like to discuss wave equation solution in cylindrical coordinates. We already discussed wave equation solution in rectangular coordinate system. So in general, the solution can be regarded as the product of 3 one-dimensional wave equation solutions. So which is not very difficult to operate. The general solution for one-dimensional wave equation can be either traveling waves or standing waves, and which are represented in exponentials or hypercosine and hypersine functions. However, for wave equation solution in cylindrical coordinate systems, it seems a little bit complicated, and I bet most of you this may be the first time for you guys to look into this kind of problems. However, for wave propagation in space, the cylindrical solution is important as well. It's important as well when it comes to transmission line propagation in coaxial cables or cylindrical waveguides, or when it comes to scattering problems from long wires, radiation from long wires like dipoles, or scattering from cylindrical objects such as aircrafts or missiles. The solution in cylindrical coordinates become very important. And the solution, wave equation solution in cylindrical coordinate system is particularly related to the so-called Bessel function. I don't know how many of you still remember the Bessel functions when in your undergraduate engineering mathematics. Okay, I bet. Well, including me, when I first encountered the Bessel function, I don't know what the heck is that. What is the application of this? Well, the Bessel function are solutions in wave equation solution, are the basics of wave equation solution in cylindrical coordinate system. Okay, so and today we will look into this. So first, let's look into the 3-dimensional wave equation that is shown on the very top of the slide, and of course you can replace phi with electrical field intensity. And however, if you perform the Laplacian operation, this is the Laplacian of a vector E. In cylindrical coordinate system, you ended up with this thing. So again, the first part is the spatial second-order derivative. The second term is the time domain second-order derivative. For a cylindrical coordinate system, the z-axis dependence is decoupled with the other two, with rho and phi. So for the z component, the Laplacian of Ez equals to the scalar Laplacian of Ez by itself. Okay, so if you replace Ez with Hz, the z direction propagation still holds in the form of one-dimensional wave equation. However, the second-order derivative, the Laplacian of E low term and E phi term, the low direction component and phi direction component are not that simple. They cannot be substituted with scalar Laplacian of the E low component and E phi component. in cylindrical coordinate system, spatial derivative of low direction and phi direction need to be operated together. They are coupled. So the Laplacian operator in cylindrical coordinate system is actually in this format. So you see the low z component, the second order low z differentiation is separated from the rest of the two. You have the second order derivative of low, you have the second order derivative of phi accompanied with the 1 over low to the square term. And the most problem comes with this. You have the you have this additional term, this 1 over low, and you only have the first order derivative of low, not second order derivative, as you observe in the Cartesian coordinate system. As a result, you can, again, we still attempt to use the separation of variable techniques, that is, representing the total solution with products of solution in individual direction. So phi r, we try to replace phi r with f low, f of low, g of phi, and h of z. And however, in the cylindrical coordinate systems, they are coupled. So we replace phi with f times g times h, and we try to modify this equation, the Laplacian equations, and we try to apply the Laplacian operator into the wave equation. So we have this result. Okay, and again, the z component is separate from the other two, while for f and g, which have low and phi involves, are coupled. They have 3 terms instead of 2. So we first apply FGH, we replace phi with FGH into the wave equation, and we divided the derivative differentiated result with FGH like this. And we can further replace the differentiation result with propagation constant. So gamma z is the projection of propagation constant gamma on the z direction. So we can do that because z-axis dependence is separated from the other two axes. Okay, so this can be replaced with so we kind of taking out of the z component, or we replace the second order derivative of h with the gamma z. Okay, so it's replaced with so in the red dash box is actually the propagation constant on the other direction, that is the gamma minus gamma z to the square. Okay. All right. So here we get rid of h. We replace the h dependence with gamma and gamma z to the square, and we try to solve the rest of the wave equation. So here we have here we introduced second tour, another tour here. The 1 over g times second order derivative of g with respective of phi is replaced with minus m to the square. M stands for the mode on the phi direction. Why this method is valid? think about that. The phi variation range in the cylindrical coordinate system is from 0 to 2 pi, or 0 degree to 360 degree. The variation of phi is only applicable between 0 and 360 degree, between 0 and 2 pi. So which means a valid solution in the phi direction must repeat itself at the same position. 也就是说，因为 phi 的变动范围只有0到2派，所以你的一个合法的答案必须要在同样的地方是同样的值。所以意思说，它绕一圈回来之后，它要用同样的形式再重复它的值。也就是说，它的答案不会是连续变动的，它的答案会是 discrete， 是会是一个一个的模态。所以我们用 m 来去代表 phi 方向上面变动的合理的结果，合理的模态。所以这个 m 你可以理解成在 phi 方向合乎 wave equation 在 phi 方向上面合理变动的模态。所以 m 当然答案不止一个。m 的话应该是一个实数，应该是一个质数，实数代表的是在 phi 方向上面变动的合法的模态。Okay, so m should be real numbers, real integers, on the which represents the modes on the phi that is applicable to describe phase variation in the phi direction. Because phi variation range is limited to 0 to 2 pi. So you want to have discrete modes that can provide satisfying result in describing the phi axis variation. So we replace the whole term with minus m to the square. So the previous equation can be replaced like this. Okay, so the third term is kind of constant in discrete form, and you have this is a second order differential equation, and it's in the form of a second order Bessel differential equations. You have f second order derivative of f with respect to rho, and you have fourth order differentiation of f with respect to rho, and the third is the constant term, which is so this is the zeroth order term, this is the first order term, and this is the second order term. So the equation now is comply with the second order Bessel differential equation. Therefore, we can introduce the general solution for Bessel equations. So Bessel functions, they are so-called the Bessel function. So aj plus by are the Bessel functions. They are the general solutions for cylindrical for wave equation in cylindrical coordinate system along the low direction. 所以这个 Bessel function 可以用来描述驻坐标系统里头沿着 low 方向变化的电场跟磁场。Okay? So Jm and Ym are mth order Bessel function of the first kind and second kind, respectively. And down here, we plot the Bessel function of the first kind, the variation of Bessel function of the first kind in space. So the horizontal axis is the number of the variant, 变数的大小，变数。 And the vertical axis is a number between 1 and -1, and the black line is the zeroth order of Bessel function of the first kind. This is the first order of Bessel function of the first kind. This is the second order of Bessel function of the first kind. One distinctive difference between those Bessel function of the first kind is J sub 0. The zeroth order solution is 0 at x equal to 0. While for other Bessel function, when x is 0, the solution of the first order, second order, and third order of Bessel function of the first kind are all zeros. So that's the main difference. The Bessel function of the zeroth order of Bessel function of the first kind equals to 1 when dou equals to 0. And the application, the usage of these solutions are particularly important to discuss for transmission line, including cables, coaxial cables, and circular waveguide when x is a small number. So that's the reason why I draw a dashed line over here. When x is a small number, it's applicable to describe low direction variation in E and H field within coaxial cables and waveguides. When x is a large number, it's applicable to describe EM fields along the low direction for propagating in free space. So what kind of problem is applicable? Say if it's an antenna problem, if you have a dipole, the radiation towards this side can be described using Bessel function. Okay? And you may be confused why not using spherical coordinate system but using cylindrical coordinate system instead. One situation is you have a very long wire, not just the half wavelength dipole, okay? And your distance from the distance from the observation points to the antenna is not that small. The other situation is if you have a missile. Okay, 画得有点丑了哈，有一颗飞弹。If you have a missile and you have an incident wave coming from the sides, the scattering of the missile of the incoming incident wave should observe this relationship, the scattering, 它的散射 should appear in the should comply with the Bessel function when you talk about the scattering of the incidence from the observing from the sides. Okay, so that is the other application of this technique. All right, so that's the Bessel function of the first kind and the second kind. This is the solution. This figure draws the Bessel function of the second kind, y, of difference order. So you can have m, when m equal to 0, the y sub 0, that is the zeroth order of the Bessel function of the second kind, well, they approaches to minus infinity. Okay, here we have another. This gamma is not the gamma we refer to. I'm sorry about that. This gamma is the so-called well, it's the exponential of the Euler constant. Euler 常数 Euler's constant is 0.577, and the exponential of it is 1.781. So actually this number is 1.781, okay, and the low, gamma low is the the projection of the propagation constant on the low direction. Low is the distance from the z-axis. Okay, so as you can see here from according to the plot, no matter is zeroth order, first order, second order, and third order, all of the solution of the Bessel function of the second kind goes to minus infinity when low approaches to 0. Okay, and when low is a large number, it can be approximate with this log relationship. 不好意思哦，所以这个 log relationship 它的用途是在 low 值很大的时候，当 low 值很小的时候，它们都会趋于负无限大。Okay, so again, when low is a small number approaching to 0, the result of the Bessel function of the second kind all approaches to minus infinity. On the other hand, when low is a large number, it can be approximated with a log function like this, 2 over pi times the log of gamma low times low times gamma, okay, where gamma is a constant number of 1.781. Taking another look at the result, taking another look at those curves, did you find that when low is a large number, this curve variation shall approach to sinusoidal functions, right? Okay, so when low is a large number, the solution of the Bessel function of the second kind approaches to sinusoidal function. This is also true for Bessel function of the first kind. As you can see here, as x become larger and larger, the variation here approaches to sinusoidal function as well, while the magnitude becomes a little bit smaller as x goes up, but they look like sinusoidal function, right? Okay, so here is the summary of the Bessel function of the first kind and the second kind. So for m's greater than 0, I mean the first order, second order, and third order, when low equals to 0, approaches to 0, the Bessel function of the first kind approaches to 0 as well. The Bessel function of the second kind approaches to minus infinity. Okay, you can substitute these two equations for them. On the other hand, for Bessel function of the first kind and second kind, as low approaches to infinity, for large low number, the Bessel function of the first kind approaches to cosine function, and the Bessel function of the second kind approaches to sine function. In other words, they are kind of similar to standing wave solution in one-dimensional problem, right? The standing wave solution for one-dimensional problem is hypercosine and hypersine. So the Bessel function of the first kind and Bessel function of the second kind, the combination of the two is suitable, is particularly suitable to describe wave behavior in cylindrical cavity, because they act like a standing wave for large low numbers. 所以这一页的话，我们总结一下 Bessel function of the first kind and second kind 在柱坐标系统里头的一般解。那你会看到，当 low 值变大的时候，它会趋近于 cosine 跟 sine 的 variation， first kind 跟 second kind。那假如你去类比于一维的直线传播的波动方程式的话，它其实就比较像是一个 standing wave 的解的形式。那既然有 standing wave 解的形式，那我是不是应该也要有 traveling wave 的解的形式？没有错，在柱坐标系统里头，你也可以找到 traveling wave 的解的形式。So 那这边的话，我们先看到了哈，就是说这个是 standing wave 的形式啊，哈 ，for large, it look like the Bessel function of the first kind and the second kind all looks like standing wave for large low numbers, and so we already observed the standing wave solution for Bessel functions for wave equation solution in cylindrical coordinate systems. Now let's see, can we have traveling wave representation in the cylindrical coordinate system for wave equations? Yes, we do. The general solution for traveling waves in cylindrical coordinate system can be comprises the so-called Hankel function. So here is the Hankel function of the first kind and Hankel function of the second kind. In fact, Hankel functions are summation of Bessel functions. So this is the definition. The Bessel function, the mth order Hankel function of the first kind is the summation of Jm plus Jym. So it's the composition of a Bessel function of the first kind and the Bessel function of a second kind. So, and Hankel function of the second kind is the composition of Bessel function. Hankel function of the second kind is the sum of Bessel function of first kind minus J times Bessel function of the second kind. For large low number, as we seen in the previous slides, Bessel function of the first kind approaches to cosine function, right? Bessel function of the second kind approaches to sine function. So the Hankel function of the first kind looks like a cosine plus J sine, and the Bessel function of the second kind, Hankel function of the second kind looks like cosine minus J sine. So does it looks like exponential Jx, and the Hankel function of the second kind looks like exponential of minus Jx. Okay, and we know that exponential Jx and exponential minus Jx is applicable for representing traveling wave in one-dimensional problem. So similarly, Hankel function of the first kind and the Hankel function of the second kind are applicable to describe traveling wave in cylindrical coordinate system in the low direction. Okay, so Hankel function of the first kind looks like traveling wave toward the minus low direction, and the Hankel function of the second kind looks like traveling wave toward the positive low direction. Okay. Okay, so here's the definition of the composition of a Hankel function of the nth order. We know that the Bessel function of the first kind approaches to cosine function, and Bessel function of the second kind approaches to sine function. So we use the large number approximation for Bessel function of the first kind and second kind. They can be composed to have this. Okay, so from the previous slide, combining the Bessel function of the first kind and second kind, you have Hankel function of the first kind looks like exponential plus J blah blah in here, and the Hankel function of the second kind looks like exponential minus J times dou with some offset in the position. So Hankel function of the first kind can represent traveling wave in the minus low direction, and Hankel function of the second kind can represent traveling wave in the positive low direction when low is a large number. So they are suitable for describing wave propagation from line source or line target, scattering from line target in free space. And finally, let's take a look at the solution in the phi direction. As already mentioned earlier, that because the phi variation is only between 0 to 2 pi, 0 to 360 degrees, only a few number of modes can survive in the phi domain. So you don't have a continuous solution. You have only separate. You have distinctive modes to satisfy the requirements for phi domain, phi axis variation. Of course, you still have the so-called traveling wave representation and standing wave representation. The traveling wave representation have the solution in the form of exponential, while the standing wave solution have the solution in the form of cosine and sine. However, only a few modes can survive because due to the restriction, the limitation in phi variation variable. Okay, so unless you have a very, very large cylinder, otherwise you only have a few modes. So 也就是说 m 的解除非你的那个圆柱体很大所以它让它的，也就是说圆柱体的那个直径远大于波长的话，那你的 m 的那个解的那个模态才会够多，你才比较有可能形成 traveling wave。不然的话，大概只要你的那个圆柱体没有很大的话，你大概只有 fundamental mode 或者是下面的几个 mode 可以存在，那多半也会是 standing wave 的形式，所以一般来讲，你的那个 second order derivative of the solution in the phi direction should appear in this form 这也就是我们前面在推导的时候把phi 方向的变动简化的一个结果了跟这个是相符的。OK， 那and lastly is the solution in the z direction, which is relatively simple in this case because it's just like the one-dimensional wave equation solution. You have hypercosine and hypersine to represent standing wave. You have exponential to represent traveling wave. Okay, so pretty much like the one-dimensional wave equation in Cartesian coordinate system. So this slide will try to we will look into a more practical problem. So first, let's look at the field solution in coaxial cable. In coaxial cable, you have an inner conductor and an outer conductor. So, and of course, in coaxial cables, the energy goes from this way or vice versa. Okay, so you can go to positive z direction or negative z direction. So the z direction is traveling wave, one-dimensional traveling wave. The phi direction variation must comply with a standing wave solution. So you can should be represented as cosine m phi plus c times cosine m phi plus d times sine m phi. So they are standing wave in the phi direction. And lastly, along the low direction, there should be standing wave. Why? Because it's bounded by the inner conductors and outer conductors. They provide a so-called boundary condition. You have no tangential E field on the surface of inner conductor and outer conductors. So for low equals to A and low equals to B, the solution of F must equal to 0. That is the so-called boundary condition. Okay, so for coaxial cables, the low variation region is between B and A. So as long as you can find the position of 0 in Bessel function of the first kind and second kind, they can be viable solution for this problem. 那我们看一下啊，从前面的看一下 ，OK， 像这个的话是 J Bessel function of the first kind. Okay, so you see they have zero crossing. So if we look into the Bessel function of the first order Bessel function of the first kind, you have zero crossing. So those zero crossing can satisfy the boundary condition. And you even the for coaxial cable, even the zeroth order of the Bessel function of first kind, you can use it to find a viable solution for that. Okay, so the field variation may be this. Okay, so this is for the coaxial cable. This is the inner conductor radius, and this is the inner outer conductor radius B. Okay, so the field variation between A and B is this. So you can use zeroth order of Bessel function to as a solution for Bessel for field variation along the low direction. Okay, and because for Y you have a zero crossing here and here, and you have zero crossing for other modes, so they can be used to synthesize the solution for coaxial cable. On the other hand, another geometry that is applicable to cylindrical coordinate system is the circular waveguide, 圆形导波管. And because the low variation range is between 0 and A, so the F solution should have no dependence, cannot include this term, the Bessel function of the second kind, because it blows up at low equal to 0. Okay, and for the Bessel function of the first kind, the zeroth order solution is not applicable. Yeah, it's applicable. Okay, it can be any number. It does not blow up. So to summarize, in this set of slides, we examine the wave equation solution in cylindrical coordinate system, and they are actually applicable to analyze real world problems. 所以虽然看起来形式有点复杂，但其实你放远一点去看或放近一点去看的话，那个 solution 其实是会趋近于 one-dimensional 的那个 problem. So even though the Bessel function, Hankel function looks a little bit scary at the first sight, but if you take the limits, you mean look within the small number region and look at the large number region, they show in the large number region it's actually approximate to one-dimensional solutions. So well, that's the application of Bessel function. They are general solution for treating problems, wave problems in cylindrical coordinate system. Okay, have fun.